The gradient of this line is also known as the slope or the first derivative. The equation of the line is y equals mx plus c, where m is the slope of the line. To calculate the slope, we need to know the difference in y over the difference in x between any 2 points on the line. We select 2 points on the line which will have the coordinates x1, y1 and x2, y2. The delta symbol stands for difference, therefore we calculate delta x as the difference between the two x coordinates, i.e. x2 minus x1, and delta y is the difference between the two y coordinates, which is y2 minus y1. Then the slope of the line is delta y over delta x, or simply stated dy by dx. Now consider a nonlinear function. The slope of the function at a point xi, yi is a line tangential to the function at that point. In this image, the black line represents the tangent and therefore the slope of the function at the point xi, yi. The slope will change along the function. This slide shows a video from the Wikipedia definition of slope. It shows the gradient of a function varying along that function. Also note where the gradient is negative, as in this case, and positive. The black line is always tangential to the function. We can approximate the slope of the function by choosing 2 points close to each other on the function and calculating the slope of the line between them. The black solid line is an approximation of the real slope of the function at xi, yi, which is the grey dotted line. As the points get closer together, the slope becomes more accurate. Also, as the points get closer together, delta x and delta y approach the value of 0. This is written as the equation where the slope of the line dy by dx is equal to the limit of delta y divided by delta x, where delta x tends to 0. This is the limit definition of a derivative. This gives us a practical way to determine the approximate gradient of a function. If we take 2 points close to each other, x1, y1 and x2, y2, then we can approximate the slope of the line by calculating dy by dx as we did for the first slide. This can be done using finite differences. First, we will look at the method of central differences. Here we take points either side of the position we want to find the gradient. In this case, x1, y1 and x2, y2 are used to approximate the gradient at xi. Secondly, we could use forward differences. Here we use xi, yi and x2, y2. Thirdly, we could use backward differences. Here we use x1, y1 and xi, yi to approximate the slope of the line at x equals xi. As a practical example, let us suppose we have an image which goes from black, which is equal to 0, to white, which is equal to 255. We will create a column of those values and visualize them as a graph. We can clearly see the edge in that graph. Now we will find the slope of that function using central differences. Delta x is 2, therefore 1 over delta x will be 0.5. Delta y is the point ahead minus the point behind, the point at which we are finding the gradient. We do not find the gradient at the first and last points. We could use forward and backward differences as special cases at those points. We will now plot the graph of that function. We can see that the peak value occurs at the highest slope in the function, which corresponds to the black to white edge. Note we could not use central differences at the first pixel, therefore we started at the second pixel. This should remind you of cross-correlation, where we start cross-correlation at the first pixel at which we can center the filter. Also, central differences is the same as applying a filter of -1, 0, 1 at each pixel in that column using cross-correlation, which looks a bit like the Sobel filters. This video shows the connection between approximating gradients and edges in images. It also shows the connection between that process and the cross-correlation algorithm. We have seen how the gradient of the line can be approximated using finite differences and how large gradients correspond to edges in images.